To take things a step further, the first thing we have to consider here is the idea of deviation, which in some contexts is also called error. And what this looks at is essentially the difference between a given data value and the supposed center, what is meant to be what you should expect it to be, which we often take, and certainly in this context, we assume to be the mean. Again, that has its strengths and weaknesses, but it's how we build things here. Where, if, for example, we have a mean of 65 and a single value of 67, then the deviation would be 67 minus 65, or 2. Then if we had something like 63, we would have 63 minus 65, or negative 2. So it's important to understand here that deviations don't need to be positive, and when they're negative, that indicates a value below the mean, where above and below, in terms of distance, is kind of meaningless, which is what comes up with the standard deviation formula, but the point here is just to make that distinction between bigger and smaller things as compared to the mean value, which is very important for further discussions, in particular of the normal distribution, but that's not something we'll get into much detail in this class. Anyway, from there, if we want to talk about the amount that something should be away from the mean, we can then talk about something like an average. And there is a value called the average deviation, but for reasons of, well, fairly deep probability theory, that's generally not what we use. In most contexts, the most commonly used measure of variation or dispersion is the standard deviation, which is meant to take something like an average deviation, but it's a bit more complex than that. Where what we do here is we take the sum of the differences, that is the sum of the deviations x minus x bar, and then square them. Squaring them allows us to focus more on the things that are farther away, and allows us to get rid of that distinction for positive and negative things, because all we care about is the distance in that case, which we then divide by the value n minus 1 and throw the whole thing under a radical, meaning we take the square root. And if we remove the square root and we put that over there as a square, we get a thing called the variance that we don't worry about too much in this class. And then you should also notice here this is an S, and that's an x bar, which means we're dealing with something in terms of a sample. For the population, the formula is slightly different because we should expect slightly less variation from a population as opposed to a sample within it, but again, a lot of these things are concerns that we don't pay as much attention to in this class. The main thing you should probably notice about this formula is that it's a little bit clunky, it's a little bit convoluted, it's a little bit to have to deal with by hand. So generally speaking, I don't expect this to be worked with by hand. I'll show one example of the sort of things you'd have to do here, but most often you really should get comfortable using a computation software to get this sort of value computed. Outside of the classroom where someone might do it once or twice to prove a point, basically no one bothers with these sort of things by hand because at best they are clunky and difficult, and at worst, which is far more often, well, computing square roots of decimal valued numbers is non-trivial at the very least, and for the vast majority of people, certainly the vast majority of my students, it's a step short of impossible, and I don't have the patience to teach you guys methods for how to do that by hand. Don't. Use a calculator. Anyway, we're going to finish this section here then by taking a look at some examples so we can get a better sense of how this sort of thing behaves.